So in this chapter, we want to talk about Newton's laws, and specifically we want to talk about forces. Okay, so we want to talk about Newton's laws and specifically forces. So in physics, okay, a force has a fairly deep meaning. Okay, but for our purposes, we can essentially define a force as a push or a pull that an object experiences. Okay, now this can be a physical push or a pull, such as if I'm pulling a wagon along the road, then I'm exerting a force on it, obviously. Or maybe the word I should say is a contact force. That would be an example of a contact force. And then gravity is an example of a non-contact force because there's not a physical rope or spring or bungee cord or anything pulling things down. It's what we call a field force. Okay, so there are two types of forces: contact forces and field forces. Contact forces are when two objects are actually in some sort of contact with each other, and field forces are when two objects, or at least one object, puts a force on another object, but they're not physically touching. They don't have to physically touch. Okay, but for our purposes, a force is either a push or a pull. Okay, so now to Newton's laws. I'm going to skip talking about Aristotle and Galileo. We talked a little bit about Galileo last time, but your book gives a fairly good description of Aristotle's view of motion. And instead of regurgitating that, I want to get straight to Newton's laws and the actual physics behind them. So what are Newton's laws? Okay, what are Newton's laws? Well, there are three of them, and he actually has a few more than that. But these are the most famous laws, and these are what are called the laws of motion. So almost any time somebody generically refers to some physics as Newton's laws, they're talking about these three laws. Okay, Newton also has the universal law of gravitation, which we'll talk about in a couple chapters, as well as the Newton's law of cooling. But when people are talking about Newton's laws, right, these are the three that they're talking about. Now, you probably know two of them, even though you may not realize you know them, right? And I don't have enough space here to write them all out as written, but I'll summarize them here and then we'll write them out. The first law is sometimes known as the law of inertia, right? And that is that an object at rest will stay at rest. So if an object is at rest, it'll stay at rest. Or if in motion, it will stay in motion. Okay, so if an object's at rest, it'll stay at rest, or if it's in motion, it'll stay in motion, unless, right, unless it's acted on by a force. Okay. Now there's a caveat here with this idea of motion. Okay. Pardon me. So when we talk about an object moving in motion, and then it will stay in that type of motion, we are talking about motion in a straight line at a constant velocity. This is sometimes called uniform motion. Okay, so another way of stating the first law is that an object at rest will stay at rest, or if an object is in uniform motion, it'll stay in uniform motion unless it's acted on by a force, unless it's acted on by a push or a pull. And I will talk a little bit about Aristotle here, just to kind of give you a sense of why this didn't necessarily come about from Aristotle's time up through Galileo's and Newton's time. If you think about it, if you push something, it will eventually come to rest, right? If you push a book across a desk or a box across the floor or something of that nature, it will eventually come to rest. So it's not intuitively obvious based on everyday experience that if an object is in uniform motion that it'll stay there. Our common everyday experience is that things tend to come to a stop. So that's one reason why Newton's first law was not necessarily discovered or thought of for several hundred years, almost 2,000 years, from the time of Aristotle up to Galileo and then Newton. But in fact, of course, now we know that the force, the push or the pull, if you will, that acts on those types of objects, a book sliding across a desk or a box sliding across a floor or something sliding down a ramp, whatever the case may be, we know that there's a new force there that's introduced. We call it friction, and it opposes the direction of motion. So in fact, if I'm pulling a wagon along, then there's the force being exerted on the wagon by myself. I'm pulling on it, but there's the force of friction that would naturally bring it to a rest if I didn't keep pulling on it. So in fact, there's two forces at work when we have two surfaces that are in contact with each other. All right? But if we are able to reduce friction to negligibility or be put in a situation where there is no friction, let's say out in space, where there is no friction, if I throw a ball out in the middle of space, and I'm going to assume we're away from any types of stars, so there's no gravity and yada blah blah blah. If I were to throw a ball in the middle of space where there's nothing else to act on it, that ball will move in a straight line, the direction that I threw it, and it will never slow down. Now that's a little... The first time you try to wrap your head around that, that doesn't always tend to make sense, but that is in fact true. And we've actually done some experiments like this out in microgravity. So we know that in fact Newton's first law is true, and we can also do it here on Earth by reducing friction down to almost near negligibility. One of the common examples would be a hockey puck sliding across ice. It would take quite a while if a good hockey player hit a puck really hard. It would take quite a while, assuming you had a large enough lake, it would be quite a while before that puck actually came to rest. It would be quite a while before it even really started to slow down very much. So if you have perfectly smooth ice and a perfectly smooth hockey puck, then friction is more or less negligible, and it will go quite some ways. So we do in fact observe the first law at work in several places every day, even though we don't necessarily realize it. Now I'm going to skip to the third law first, or I should say the third law second, and then we'll go back to the second law. But the third law, most people know, this is probably the most famous law of all, and the paraphrase for this says that for every action there's an equal and opposite reaction, right? So for every action there's an equal and opposite reaction. That's the paraphrase. In the physics sense, we typically substitute the word in force for this word action. So a more precise way to state the third law is that for every force, there is an equal and opposite force. Okay. Now this has some pretty deep implications. For instance, going back to the wagon wheel, or the wagon that I'm pulling, if I'm pulling on the wagon and I'm exerting a force on the wagon, then the wagon is exerting the exact same force on me. Okay? I want you to think about that very carefully. If I'm exerting a force on the wagon, then the wagon is exerting the exact same force on me. Now that should cause you to pause and maybe scratch your head, right? If we're putting equal forces onto each other, how in the world am I able to actually pull the wagon? Well, I'll explain that, not necessarily in this video, but in one of the lessons for this chapter, we'll get to it. So hang on to that thought for now, but I'll also mention that Newton's third law, this reactionary force law, then it is one of the most fundamental laws in physics because it is the basis for the conservation of momentum. And we'll talk about that later on in chapter 8, or chapter 7, I believe. So put this one in the back of your hat, okay? This is a very, very important law, and it's the fundamental law for a lot of deep physics that crop up, especially in things like subatomic physics and things like that. So this is an extremely important law. But, okay, and there's a reason that I skipped the second one, which is what I want to go to now. The reason I skipped the second one is because it's the main thrust of this chapter, and it's essentially what we're going to focus on through this chapter and then on into the next. It's the basis for the next two chapters. Also, it's the one that is the hardest to put into actual words. Okay, so in concept, here's what the second law means. All right, I'm going to actually draw a picture rather than write out a bunch of words. Okay, I'm going to have a box, all right, or a block, or whatever the case may be. All right, and it's going to have some mass. It's going to have a mass of capital M. All right. Now, according to the first law, if it's at rest, it will remain at rest unless I exert a force on this object. Okay. Now, let's assume that I do exactly that. All right. Let's assume that I exert a force, I attach a rope, and I pull it to the right with some force. Call it capital F. Now, what's going to happen to this box? Okay. Well, go back to the first law. If the object has a force on it, then that means that that force disrupts its uniform motion. Okay? So the box cannot simply move with a constant velocity. If it did, then it would be in uniform motion. And the only way that a object can have a force on it is if that force disrupts its uniform motion. So this means it cannot move with a constant velocity, but it must accelerate. Okay? So as a result of this force, F, this mass M must accelerate. All right, that's the meaning of the second law. Okay, now what the second law actually says, and I'm going to assume that the box and the surface that it's moving on are frictionless. Okay, the box and the surface that it's moving on are frictionless with respect to each other. Under that circumstance, if F is the only force that this box feels, then it must accelerate. And so in words, what the second law says, okay, what the second law says, and I'm going to paraphrase this as well. Your book gives a definition, but it's not necessarily intuitively obvious exactly how this works. So I'm just going to paraphrase it for you and hopefully break it down into a little bit more of a manageable language. So basically, if an object experiences a force, Okay, so far we have if an object of mass m experiences a force, it will accelerate with an acceleration a such that the acceleration and the force are proportional, and the acceleration and the mass are inversely proportional. Okay, so let's break this down just a bit. All right, and it turns out that there's a very nice simple equation that we will be able to use from this, and in fact it's the equation that more or less started the entire scientific revolution, at least is the basis for almost all of physics. But let's break this down just a little bit, and let's think about this. All right, so if an object of mass m experiences a force, then it will accelerate with an acceleration we denote by a, such that a and f are proportional, which means that as if f increases, then a increases as well, which makes sense. The larger the force or the larger the pull I put on an object, the faster it's going to accelerate. That makes sense. And a and m are inversely proportional. So if for any given object, if I exert the same force, let's say on two different objects of two different masses, right? Think of a bowling ball and a baseball, right? Two objects of the same shape but with different masses, and I apply the exact same force, right? Which one is going to accelerate faster? Well, of course it's going to be easier to accelerate the baseball than it is the bowling ball. It has less mass, it has less resistance. And so for any given force, if I put the exact same force on these two objects, then the smaller the object, the larger the acceleration. Okay, so for two objects, of different mass, but same force applied, the smaller object, or let's say the less massive object, right? The less massive object will have a larger acceleration. Okay? So mathematically what this means, all right, mathematically what this means is that if I have an object that has a force applied to it, then that force will be proportional. This is the symbol for proportional. Will be proportional to the acceleration, and the acceleration will be inversely proportional to the mass. Okay? So these are the two mathematical, they're not equations, but the two mathematical expressions that we have to encompass with this one equation that we're about to write. Okay? So for any given object, if I apply a larger f, then I'll have a larger acceleration, but for any given object, its acceleration will be inversely proportional to its mass, because the larger the mass, the smaller the acceleration. Okay? And we encompass this by this equation, and we can say that the acceleration that an object equals, or the acceleration that an object experiences, I'm sorry, is going to be equal to the force that it experiences divided by the mass. Okay? So this equation encompasses both of these expressions. A and f are directly proportional. As one gets larger, the other gets larger. And a and m are inversely proportional. A is up top on this side and m is on the bottom on this side. So as m increases, a will decrease. So this expression, a equals f over m, is the equation form of Newton's second law. Okay? Now this is not exactly how he wrote it, but this is how it's often presented in introductory texts. And we can actually further simplify this. Okay, we can further simplify this. If we multiply both sides by m, then we get the equation F equals ma. Okay, so this is the equation of equations. Okay, this is by far one of the most important equations ever written down. Okay, so we will just call this the equation. All right. Almost all of your homework problems this semester will involve either F equals ma or some derivation thereof, meaning that the equations that we use down the road will be able to be derived from this. And in fact, the kinematic equations that we saw earlier, V equals V initial plus AT, distance equals V initial t plus 1/2 AT squared, and all of those equations that we used before, we can actually derive them from this equation using the techniques of calculus. That's a bit beyond what we do here, but you can actually do it using the techniques of calculus. So I'll leave this video here at this point. In the next video, we'll actually do some examples with this equation and talk about what it means to have forces exerted on objects. Okay? So take care, and I'll see you next time.